And thank you. Sure. Bonjour.
Ça marche 2 secondes
Oui.
C'est bon, ok. Valérie, peut-être Valérie, Nicolas, peut-être. Aujourd'hui, peut-être qu'il y a encore une chose, mais on va peut-être de taille.
C'est bon, c'est bon.
Voilà.
Il y en a.
Il y en a encore. Ouais, bon. Oui, ils ont leur propre version. Yes. Stylo. Ah, là, si tu fais déjà. C'est bon? Ouais.
C'est bon.
Ah, c'est bon. Oui.
Donc, je suis enchantée d'être là avec vous aujourd'hui. Vous allez défendre vos travaux donc, portant sur la structure et l'ergologie des émulsions à base de polymères dans un solvant commun stabilisé par des copolymères. Donc, auprès du jury, donc, composé d'abord par de rapporteurs, d'accord. Donc, ici, le professeur, directrice de recherche, moi, directrice donc, de recherche, Véronique Jung, directrice du CRPP, donc l'Université de Bordeaux, du professeur donc Jung, de Pascal Blaise, donc ah non, Paris-Saclay, pardon, excusez-moi, à Paris-Saclay, veuillez m'excuser, effectivement, la faculté de pharmacie, c'est l'université de Paris-Saclay, absolument. Puis après, vous avez donc comme examinateur le professeur Jean-Luc Sitz de l'université de Lorraine, qui est ici, absolument, du laboratoire de chimie physique macromoléculaire. Puis moi-même qui viens donc de l'Université technologique de Tarbes, laboratoire de reproduction plutôt par style maternelle-mécanique et fossile. Et enfin, donc, je présente vos 3 encadrants. Donc, Vous avez ici donc le directeur de recherche je ne sais pas, je vous prie, bien, excusez-moi, de l'Institut des molécules donc, et matières premières. Vous avez Frédéric, docteur Frédéric Boulon, ici, et 20 professeurs, donc les arts qui est notre directeur. Voilà, je pense que j'ai fait le tour, donc on vous accorde en tout cas 35 minutes. Allez-y.
Merci pour l'introduction. Je vais commencer la présentation en anglais. So, good morning, everyone, and thank you for being all in this room and also on online. My name is Hyun a PhD student in EMMM at Le Mans University. Today I'll be presenting my PhD work entitled Structure and Rheology of Polymer-Based Emulsions in Common Solvent Stabilized by Copolymers. This work has been supervised by Lazare Berniagia, Taco Nicolai, and Frederic Huneau, and in collaboration with LCPN Group in Nancy, with the PhD student Sainia, supervised by Professor Jung and Khalid Gazi. First of all, I will introduce the background information of my projects for you to help you understand. Then I will begin my first project on stabilization of water in water emulsion using bis hydrophilic copolymer. Right. Then I'll move on to stabilization of PSPMMA emulsions using bis THF philic copolymer. This is also emulsion in common solvent. Then I will talk about microstructure and rheology of PSPMMA emulsions during aging. So first of all, what is emulsion? Emulsion is a mixture of two or more immiscible liquids having one dispersed phase in a continuous phase. So either liquid 1 or liquid 2, it will be inside the droplets surrounded by the other liquid. Wow. And when the emulsion is not stabilized, they will form phase separation of liquid 1 and 2. And depending on the density, they will be on top of the other. Those liquids could be water, oil, organic solvents, and others. And in one case, there is emulsion with a common solvent. Emulsion with a common solvent is when two or more polymers are in a common solvent. So both of these polymers have to be solubilized in the solvent. And at above certain concentration, they would be incompatible. And with this phase separation, we could form emulsion as well, having polymer 1 rich phase inside the droplet surrounded by polymer 2 rich phase. The common solvent could be water or even chloroform or other organic solvents. A potential application of water in water emulsion when the common solvent is water could be to be used in fat-free food products, in cosmetics to use hydrophilic ingredients, and in pharmaceutical to encapsulate bioactive ingredients. Another potential application with other organic solvent is to prepare a polymer blend and also to encapsulate in a non-aqueous media. The most important characteristic of emulsion in common solvents is that the interfacial tension is very low and the interface is very broad. That the conventional molecular surfactant that we use to stabilize immiscible liquids are not efficient anymore in this stabilization. So there have been many studies on Pickering stabilization on this emulsion in common solvent using the particles. What is Pickering stabilization? Is the stabilization mechanism to have the particles absorbed at the interface. By absorbing at the interface, the particles reduce their free energy which mainly depends on particle radius and the interfacial tension between the particle and the two phases. And so by absorbing the particles at the interface, we reduce the interfacial contact or interfacial area between the two incompatible phases. However, absorbing the particles at the interface does not always stabilize the motion. Thus, in order to enhance the stability, and furthermore, if it could resist it from dilution, we could cross-link the particles at the interface to encapsulate. One example is stabilization of water in water emulsion using microgel. In the system of pulilan in amylopectin, protein microgels was used to stabilize. Then enzyme was added to cross-link them at the interface, where these microcapsules were able to resist from dilution. Then we got this idea of what about using dilocal polymer composing of each polymers in the emulsion, because we know that then each blocks are incompatible to opposite polymers, so they would place themselves at the interface due to the incompatibility. Then forming a dense laminar layer, we could cross-link them at the interface and thus encapsulate and resist from dilution. This leads to our project webcaps. The purpose of this project is to stabilize water in water emulsion by custom synthesizing the copolymer of dextran and POE-GMA, and then cross-link them at the interface to form microcapsules and be resistant to dilution. The synthesis part of copolymer was done by Hyun, our partner, and she synthesized the dextran chain to the POE-GMA, which is a piophilic polymer, polyoligoethylene glycol metacrylate. This synthesized copolymer would be used to stabilize the dextran PO emulsion, and we would expect them to place themselves at the interface. Then by cross-linking them, we would form microcapsules, hoping that it will resist to dilution. Now I'll begin my first project, is to stabilize water in water emulsion. The system I'm working on is in dextran and PO emulsion. It has 200 kilogram per mole, the PO, and dextran has 500 kilogram per mole. On the left, it shows the phase diagram of the dextran and PO in water. And this blue curve represents the binodal, which means below binodal, the mixture forms homogeneous solution. Above this binodal, there's a phase separation where it enables the emulsion forming. And this high line represents where the interfacial tension is constant. In this project, I'll be focusing on dextran and PO emulsion at this particular volume fractions, 10%. Then, in this slide, I'll be focusing on dilocal polymer of dextran and POE-GMA, which has been synthesized by photoraft polymerization of OE-GMA units on omega position of dextran. The polymer types that's used is a 33 kilogram per mole and 300 gram per mole of OE-GMA units and 1300 gram per mole. And we also varied the POE-GMA compositions. These two are the scheme examples of the dilocal polymers. They basically have bottle brush structure. They both have 60% of POE-GMA in the composition. And on the left, it has the smaller OE-GMA units, and on the right, with the bigger OE-GMA units. With smaller OE-GMA units, the skeleton backbone of metacrylate is longer with smaller brushes. And with 1300 gram per mole OE-GMA units, it has shorter skeleton and longer brushes. Here I'll be talking about the smaller OE-GMA unit first at 60% of POE-GMA in the composition. And at concentration of 0.1%, I used it to stabilize 10% volume fractions dextran in PO emulsion. At fresh initial state, the droplet radius was about 7 microns. And within a day, the droplet sizes increased, which means there was a coalescence, and they sedimented to the lower phase because dextran is more dense than PO phase. And the droplet size increased from 7 micron radius to 35 microns. Then within a week, they remained stable. That the droplet radius barely increased from 35 to 39 micron. Then I studied in different POGMA compositions. In all compositions, I observed very similar stabilization mechanism that within a day, they coalesced and sedimented. And for a week, at least a week, they remained stable. From 40 to 70% POGMA composition, the diblockopolymers are labeled with RBITC, and they are labeled on dextran. So they are highlighting the dextran phase. But on the 80%, it is not labeled. Thus, I added rhodamine, which prefers PO phase, and thus it's highlighting the PO phase, the continuous phase. So we can say that the copolymers are effective in emulsion stabilization. And here I studied with larger OEGMA units. And I observed very similar stabilization mechanism that within a day, they coalesced and sedimented, and for at least a week, they remain stable. However, the only difference is that the droplet size or the radius, they tripled by the size. So we can say that smaller OEGMA units is more efficient in emulsion stabilization. Then at 60% of POGMA composition at smaller OEGMA unit, I studied the effective concentration. Previously, I showed concentration at 0.1%, where they were stable and sedimented. And I lowered the concentration to 0.03%, which there was a phase separation of dextran phase, which means there was not enough glucopolymers to prevent coalescence. Then I increased the concentration to 1%, where I observed much smaller size of droplets and no sedimentation. This means that the glucopolymers were enough to cover the droplets and prevent coalescence, thus prevent droplet growth, and thus prevent sedimentation. Now that we understand that copolymers are effective in stabilization, we wanted to understand how. Using the same copolymer and on the emulsion that were stabilized, I looked into the surface of the droplets where I observed particles surrounding the surface. And thus, we could assume that those particles surrounding the droplets are preventing the coalescence. Thus, we could conclude that this stabilization is due to Pickering stabilization, which isn't exactly what we initially intended to do. However, they are still effective in emulsion stabilization. Thus, I continued the characterization. We wanted to understand where these Pickering particles are coming from. So I added 1% of the glucopolymer in the dextran solution, where there was a phase separation. The copolymer is labeled, thus this highlighted phase separation is the phase separated copolymers, and the lower phase would be the dextran. However, this is not complete phase separation, because when I looked into the concentration of the copolymers in both phases, I observed 1.8% of copolymer and 0.6% of copolymer, which means that there are still solubilized copolymers in the dextran phase. Thus, this could mean that there's a heterogeneity of composition in this one copolymer. And this is the image of the phase separation. You can see that it is a very small portion that phase separates. And when I diluted the system, it formed the homogeneous solution. Thus, there was no aggregate formation. Then these copolymers were inserted in PO solution, where I observed a lot of particles. And I diluted them, and I still observed those particles, which means they are resistant to dilution. And thus, these particles would have covered the droplets and thus stabilized the motion. Then I studied the stabilization effects on varied PO molecular weight. Initially, in my system, it had 200 kilogram per mole of PO, and in the presence of copolymer, it was stable. Then when I reduced the PO molecular weight to 100, they phase separated within a day, even in the presence of copolymer, and always at the same concentration. And when I even further decreased the molecular weight, they destabilized within 3 hours. And I wanted to understand why, so I looked into the mixture of glucopolymers in corresponding molecular weight PEO solutions, where I observed decrease in the number of aggregates. And thus, we could conclude that decrease in number of aggregates lead to decrease in stabilization effect. And I studied the resistance to dilution. This droplets that I previously shown were diluted to dilution factor of 1.2, 1.5, and 2.0. And apparently, at dilution factor of 2.0, which is still above binodal, they phase separated within 4 hours. Why? Because interfacial tension, if you look at the phase diagram, is proportional to the tie line length to the power of 4, which the tie line length is directly proportional to the dilution factor. So by having the dilution factor of 2.0, the interfacial tension would have decreased by the factor of 16. And thus, the emulsion destabilized with the dilution. In conclusion, for this part of the project, is that dextran PEO emulsion was able to be stabilized by diblocopolymer of dextran POE-GMA. They quelled within a day and sedimented and remained there for a week. And we observed aggregate formation of copolymers in PEO solution. And thus those aggregates cover the droplets and thus have Pickering effect. However, these copolymers were not effective in stabilizing PEO in dextran emulsion, and the reason remains still unclear. Also, we tried to move on with the cross-linking as we've initially intended to do. However, when we tried to cross-link them, it didn't cross-link it at the interface, but throughout the bulk. So they aggregated and they didn't be resistant to dilution. But still, we were still curious if the diblocopolymer composing of each polymers could stabilize the emulsion in common solvent by forming laminar layers. So I worked in a different system. This system has polystyrene and polymethyl methacrylate, PMMA, and they have a very similar molecular weight and huge, 370 and 350 kilogram per mole. On the left, I made this phase diagram of PS and PMMA in the organic solvent of THS. And again, the blue curve represents the binodal, and above binodal, this tie line, where this point represents different volume fractions where I studied the emulsion stabilization. The glucopolymers I used are diblocopolymer of PS and PMMA. The weight ratio is about 50-50, and the total molecular weight is 1,800 kilogram per mole, which means each block is double the size of the homopolymer. I also studied the symmetrical diblocopolymer, which has 80% of polystyrene and a very similar total molecular weight. Using the 50-50 diblocopolymer and at concentration of 0.1%, I stabilized the PS-PMMA emulsion at different volume fractions. These are the emulsions at initial state. And the droplet sizes radius corresponded to the volume fractions, regardless of which polymers are inside the droplet. So at 1090, the droplet radius were about 1 micron. 2575, the droplet sizes were about 3 microns. After a week, the droplet sizes barely increased. That at 1090, the droplet radius increased from about 1 to 2.6 microns. Then at 2575, they increased from about 3 to 5 to 7 microns, which is a very small increase. And it means that the emulsions remained very stable for a week. And also, this slight increase of the droplet size would have happened initially while waiting for the dye blocks to place themselves at the interface. And thus, we assume the stabilization is due to the placing the dye block of polymers at the interface, because we know that at this very small concentration, there is no effect of viscosity. And we wanted to prove scientifically, so I performed light scattering measurements. At same concentration of dye block of polymer, I varied the polystyrene concentration. So these are a mixture of dye block in PS solution. From 6 to 12% of polystyrene, the excess intensity, scattering intensity, was low, and there was no Q dependency, which means the mixtures formed homogeneous solution. Then when I increased the concentration, there was a high excess intensity observed, and as well as high Q dependency, which means there was a big aggregates forming. And in transient concentration, we observed the increasing of the Q dependency and the scattering intensity, which shows the mixture of the aggregate in the homopolymers homogeneous solution. The scattering intensity at the lowest Q were taken to another graph in the function of polystyrene concentration, where I observed slight decrease in the intensity in the beginning because there is a contrast difference. The contrast between the dye block and THF is bigger than the contrast between the dye block and polystyrene because the dye block itself consists of the polystyrene, and that it causes the decrease in the scattering intensity. Then after a certain concentration, which now we will call CMC, critical micelle concentration, there was a broad increase in the intensity, meaning there's a formation of aggregates, and in this case, we will call it micelle. So we could assume that dye block forming micelles in the polystyrene solution would have polystyrene block at the corona, having the PMMA block inside the core. And when I performed exactly the same measurements in PMMA solution, I observed a very similar pattern of scattering intensity. And thus we could deduce that the micelle formation would have PMMA block at the corona and PS inside it. And the CMC in each solutions would have 8 to 10% in polystyrene and 10 to 12% in PMMA. And the aggregation number was calculated by dividing the maximum scattering intensity by the lowest scattering intensity, which turned out to be about 1,000 in both solutions. And the RGO was also calculated. At polystyrene, it was 0.4 microns and 0.7 microns in PMMA. In polystyrene, it is smaller, probably due to the rigidness of the polystyrene polymers at the corona. Now that we understood the micellization of the dye block, I added the PMMA polymers. At the same concentration of dye block and at the concentration of polystyrene above CMC, I entered 0 to 0.2% of PMMA. And this system is still above binodal, so there should be a phase separation. Without PMMA, there was no Q dependency, and it showed low scattering intensity. Then when I entered PMMA to 0.05%, the Q dependency increased as well as the excess scattering intensity, which means that PMMA polymers entered inside the micelles due to the compatibility with the PMMA block inside the core, thus causing the micelle swelling. and further increase of PMMA concentration to 0.2%. It increased the Q dependency and the scattering intensity even further, thus increasing the size. Further increase of the concentration of PMMA was not able to be measured through light scattering because the size of the micelles were too big, and thus I move on to confocal, where I could observe PMMA in PS emulsion. Here I studied the effect of asymmetrical diblocker polymer, which has 80% of polystyrene and similar total molecular weight, and I studied it on 2575 volume fractions in the emulsion. In PMMA continuous phase, the emulsion destabilized within 3 days, and the micellization of this diblock would have the longer PS block inside the core because it is incompatible in the PMMA continuous phase. But in PMMA in PS solution, which is having the PS as a continuous phase, the emulsion remained very stable, that the droplets barely increased within a week. Thus, we could assume that longer PS block would have placed themselves at the corner inside them in the micelles. Thus, we could conclude that with a symmetrical diblocker polymer, the emulsion is more stable when longer block is placed at the corner. In conclusion to this part of the project, diblocker polymers was able to form micelles in each homopolymer solutions at the concentration above CMC. And when opponent polymer was inserted, it caused the micelle to swell by entering inside the core of the micelles due to the compatibility. And using the asymmetrical diblocker polymer, having the longer block placed at the corona stabilized the emulsion better. Now that we understood the emulsion stabilization using the diblocker polymer, we wanted to study the evolution of the emulsion during aging. Thus, we used the same system of PS and PMMA emulsions to study the microstructure and rheology, but we used different solvents because CHF has a boiling point of 70 degrees, so it's very volatile to use it in the rheologic measurements. Thus, I used dibenzene ether, which has a boiling point of 300 degrees Celsius. In this slide, I show the destabilization of PS-PMMA emulsion in this solvent. The volume fraction is always 2575. Here I show the confocal images. At 20 minutes, the radius of the droplets were about 17.5 microns. And within 1 hour, 30 minutes, there was a creaming happening, and PS phase is less dense than PMMA, and thus the bigger droplets go to the upper phase. And this creaming and coalescence continued to happen with time, that within a day, there was a full phase separation. I studied the same system in oscillatory shear measurements. This measurement was conducted for 12 hours at 0.05 Pascal, which is within the linear region. And across the whole angular frequency, G double prime was always superior to G prime. It shows the liquid-like behavior. The relaxation at the lower frequency shows the droplet relaxation. And at higher frequency, it shows the fast relaxation of the polymers and very small droplets. And we can see the indication of droplet growth with time, that the black curve at 12 minutes would shift to the blue triangular curve. And the shift is to the left and downward with time. So this shift were made into a 1 method curve during 4 hours. And this method curve only contains until 4 hours because furthermore, afterwards, the droplet size increased too much and there was a creaming, and thus it was impossible to plot it in the master curve. And this master curve has a time reference at 12 minutes. From this master curve, I extracted horizontal and vertical shift factors, where we could see that they very much correspond to each other, which means that the complex viscosity barely changes. And we could see there's an abrupt increase in the shift factors within first 3 hours. So there's a fast relaxation of the droplets within 3 hours. Now that we've studied the qualitative evolution of emotion during aging, I would like to study quantitatively, thus introduce the Pallier model. Pallier model connects dynamic modulus of emotion, having dynamic moduli of each two phases, droplet phase and continuous phase, droplet radius, and interfacial tension. In this model, the most important parameters are the volume fractions and gamma over R. The master curve that I've made previously would fit into the Pallier model until 10 radian per second, because above 10 radian per second, there was a diversion and it wasn't possible to fit it to the Pallier model. And this fit, thanks, I got the help from François Labbé from a different lab. And I was able to extract the R over gamma distribution from this fit, and it showed the average R over gamma of 1.7 meter squared per Newton. And in this distribution, having known that the interfacial tension is constant, it should be proportional to the distribution of the radius. However, it shows two binary peaks or populations, which is an artifact, because from the confocal images, we know that there is a broad continuous distribution of the sizes. And from confocal images, we got the average radius, droplet radius, which is 17 micro. Thus, we could calculate the interfacial tension at 10 micronewton per meter, which this value is within the range of other interfacial tensions in other emotion in common solvent systems. Now that I've studied the oscillatory shear measurements, and I've studied the aging of the emotion in flow curves, after 47 minutes of aging, I conducted the flow curve from lowest flow shear rates to highest shear rates. And with increasing shear rates, the viscosity decreased, which shows that there's a structural changes. And the structural changes could be seen in detail in this confocal images. Right. Where, sorry. Steady shear was applied on the emotion. And from the confocal images, at 0.03 second minus 1 to 0.05 second minus 1, we could see the flow of the spherical shapes of droplets in the direction of the flow. And from 0.09 to 0.3 second minus 1, we could see there's an elongation of the droplets and alignment. And at above 0.9 second minus 1, they form strand-like morphologies. After the steady shear was put at the rest, this elongated or even strand-like morphologies break into small pieces and reform back to spherical shapes. That, for example, at 0.3 second minus 1, the droplets were put at the rest, and after 35 seconds, they form back to the spherical shapes. So this is a shear-induced rejuvenation. So after flow curve, it's impossible to look at the aging of the emotion. So if we correspond this flow curve to the confocal images, you can see that at 0.05 second minus 1, the droplets formed are still spherical. 0.09 second minus 1, they will start to form alignments. And even at 0.3 second minus 1, then at this is the alignment. And at 0.9 second minus 1, they show the strands. Thus, at each point of the flow curve, there is a structural changes. Now that we've conducted both complex viscosity and shear viscosity, we wanted to compare them. By the Cox-Mears rule, if there is no modification of morphologies due to shear flow, they should be equal to each other. However, we would see here, in this measurement, I conducted flow measurements right after the oscillation measurement. So after 37 minutes of aging, oscillation measurement was done. And then afterwards, flow measurement was done at 47 minutes. And 94 minutes of aging, and then I conducted oscillation measurement. Afterwards, I performed flow measurements and so on. At 37 minutes, the oscillation measurement corresponded to the flow curve, probably because there was not much aging being done, so the droplet sizes were very small, and thus even with the structural changes, the relaxation the droplet sizes were similar in both oscillation and flow curve. But with aging, we could see that there was a slower aging observed in the flow curve. Then these complex viscosities and the shear viscosities were put into one master curve, and surprisingly, all data could be shifted to a single master curve. And I extracted the shift factors from this master curve, where I observed slower aging in the flow curve. So, in conclusion, aging of emulsion was observed through oscillation shear measurement. And from this oscillation measurement, the shifting of the G prime and G double prime showed the droplet growth. And distribution R was extracted from fitting the G prime and G double prime curve to the Hyun model when the, there should be no dot, interfacial tension is known. Droplets elongate in shear flow and could form long strands with increasing shear rates. And when I compared the complex and shear viscosity, they were able to be superimposed together. And there was a shear flow where it could rejuvenate the emulsion. The general conclusion of my PhD work is that dextran PO emulsion could be stabilized by the diblocker polymer of dextran and PO by forming the particles in PO solution. In the system of PSP-MMA emulsion, the diblocker polymer was able to stabilize this system by forming the micelles at each homopolymer solutions at the concentration above CMC. Then the evolution of emulsion under aging was able to be studied using the rheological measurements. Shift factors of G prime and G double prime in the master curve shows the evolution of emulsion. The interfacial tension was able to be deduced by Hyun model by the parameters of volume fractions and R over gamma. And during shear flow, the droplets deform from spherical to aligned strands with increasing shear rates. Perspective of my work is that first, for stabilization of emulsion with common solvent, it will be interesting to use more compatible polymer to PO than PO-EGMA to not form aggregates, because PO-EGMA is a pretty rigid polymer. So if we could have a more flexible polymer to place the diblocker polymer at the interface and then thus cross-link them, it will be more applicable. Other stimuli responsive biopolymers could also be used to form laminar layers and then to create smart emulsions, which would be responsive to other physical-chemical properties in different pH and temperature. And other than water, applying green solvents would be more applicable in bioindustry. Also, in the study of PSP-MMA emulsion area in rheology measurements, I did a preliminary experiment when the emulsion is stabilized by the diblocker polymer. And we observed slower shift, smaller shift within 46 hours. Thus, it will be interesting to look into the Auer gamma or even the interfacial tension with and without the dipole copolymer when we fit it to the polymer model. And also, it will be interesting to fit this polymer model with a continuous size distribution because we observed that there is an artifact of the binary population, and we know that it is not true. So it will be interesting to have more exact distribution. Thank you all for your attentions. And if you have questions, please ask away.
Merci pour votre présentation très posée et illustrée avec des supports formidables qui je me présente. Merci. Donc, vous donner la parole à des journalistes pour problème.
D'accord.
On va attendre. So first of all, I would like to thank you and your supervisor for inviting me. I was very interested in the topic, so it was very nice to read your manuscript and also to hear to see your presentation today. And I really would like to congratulate you for the presentation because it was very nice. I think there was more explanations than in your manuscript, so it was easier to follow. And you also chose not to have exactly the same chronology of presentation, so it was. So maybe I will keep the same order than you presented here, rather than the manuscript. And first of all, if we consider the system of Dijkstrand and Pinot, yes. So you very well explained the nonsense. Yes, you have no resistance to dilution, sorry. Yes. So your emissions that are stabilized when you dilute them, they are not stable anymore. If I understood correctly.
Yes, exactly.
And you explained that when you dilute, you change the timeline.
Yes.
So you decrease interfacial tension. Does this mean that, in your opinion, the fact that you destabilize the emission is because you decrease the anchoring energy of the particle at the interface? Or do you think that you dilute your particles and they just disappear? They dissolve. So what is the reason of this non-resistance to dilution in your opinion?
First of all, even without the dye block, when we dilute the emulsion and common solvent, the interfacial tension decreases.
Yes.
Because the concentration
closer to the
yes.
homogeneous phase, yes.
Yes, the concentration of each phase decreases. And during this dilution, the concentration of dye block was kept constant at 0.1%. And thus, we could assume that it's probably due to the interfacial.
The total amount of okay, so you kept the amount
of copolymers.
Copolymer that do the aggregate. Do you still have the aggregate when you change the composition of the different phases?
Yes, because we observed this aggregates at the interface. And
so
yes.
Why do you lose the stability when you dilute?
Because the concentration is too low and there's much more miscibility between the two phases, PO and dextran, and there's tension is too low for the particles.
So does it
to
mean
stabilize
that the particles that were absorbed, the energy to keep them at the interface decreases?
Yes, exactly. So, um,
Have you tried to look at your particles after this phase separation when you have the deletion? And are the particles still there?
yes, because they still stay at the interface, because you see this highlighted particles and they form.
But you have less interfaces, so do you have an excess of particles compared to the amount of interface? Or?
Actually, those particles that are formed to stabilize the motion, the amount is very small. So even
Yes, okay, but then you just said they remain at the interface when you have the phase separation.
yes,
So this means that it's not the energy that decreases, it's still enough to stay at the interface. So in your opinion, do you have an idea about the mechanism of destabilization or why it destabilizes? Because usually a dilute emulsion is more stable than a more concentrated emulsion, so it's I don't know.
yes.
Maybe the question is too complex.
I think it'll be interesting to think about it and then to add more comments in the manuscript about it.
If I switch to the system with polystyrene and PMA,
Yes.
show nicely the different micelles. Oh, the first thing I really appreciated the phase diagram that you plotted in the manuscript.
Thank you.
And I was just curious about how you determine it, because you said you have the phase separation, you look at the different volume, but this is not enough because you can have a polymer rich, so it's not exactly the pure system, so the volume is not enough. So how did you, in practical, how did you establish the phase diagram?
So yes, it's true that the both phases are still miscible to each other. So even though there is a phase separation, the phase separated phases wouldn't be pure, but we would assume it to be pure. And so when I did it in the practical experiences, I mixed at the random concentration where I assume it to be 50-50, and then I mix them, centrifuge them to phase separate and take out each of the phases. And then we mix them at each volume fractions 10, 19, 25, 75 and make the tie line. And thus we can assume that each phases would be not pure, but still the volume fractions is made by the volume. Yes.
If I go to either, I think it was slide 28 or 30, maybe I didn't catch how you did the link between the micelles, because it's very clear about the micelles.
Yes.
But how do you make the link between the micelles and the emulsions? So in your opinion, is it just swelling of micelles up to having the emulsions, or is it something different? So what happens to?
Yes, exactly. That's what I'm assuming. That when we increase the concentration upon a polymer, it would continue to go inside the micelles because it is incompatible with the polystyrene blocks. And thus it would continue to grow the size, and thus it will form a droplet.
Okay.
Yes.
So have you an idea why your emulsions are more stable when the block which is outside, is lowest. So when you are completely equilibrated, it's
Yeah.
less stable than when one block, when in the asymmetric case.
Because we assume with the longer block, and because its polymers are flexible, we would assume there is a steric repulsions. And well, there would be interactions, van der Waals interactions, but the steric repulsion would be the dominant one, and thus forming more steric, denser steric barrier, and thus stabilize the micelles, emulsions, droplets better.
But you don't really have the opposite when you have the other copolymer.
Yes, in the manuscript, I showed the opposite
Yes.
composition, but probably that's because it has 1,000 kilogram per mole higher total molecular weight, so it was very big enough, and thus it stabilized both PSPMA and PMA and PS emulsions. So that effective molecular weight was bigger than the compositions.
And with the experience that you now have about these systems, do you have some rules, or do you have any idea of predicting which polymer should be used to better stabilize the emulsions?
Actually, that's the purpose where we started with the idea of diabloco polymer to stabilize the emulsion in common solvent was to use the polymers of the homopolymers.
Yes.
Thus, the criteria for the dibloco polymer is to be composing each homopolymers. But to have that diblock, each homopolymers would have to be incompatible to each other and have to be soluble in a common solvent. So that when I started this project, that was a pretty challenge to find the polymers that are accessible in a short period of time and to find the solvent.
If I now switch to the system where you are looking at shearing during,
Yes.
I think it was slide 39. Here, if I understood correctly, you explained that you have strong, when you increase at the beginning, you just deform a little, but not very much. You have spherical drops.
Yes.
And then you deform your drops until they align. And at the end, you have strong like morphologies.
Yes.
I think you showed one case where you have stopped the shear. Yes, this one. And you have this picture. But when we compare the size that are obtained after shearing, it is very close to the one
On the left.
at the beginning, no? So
Yeah.
did you really have a fragmentation here? Because what do you name rejuvenation? Is it just that you have fragment your emulsion?
Yes, because with normally, no, not normally, because after the shear, the structure completely changed, and then they broke down into again droplets. So it means that the droplet shapes are going back to that spherical shapes, and that's not showing the aging effect. That's what I wanted to imply with the rejuvenation.
But have you compared the size after shear cessation and before shearing? And do you have an evolution of the droplet size?
I didn't exactly measure the droplet size before and after, but when I looked into it, they slightly increased, but they corresponded to the droplet size before the shear.
Yes, so you didn't observe any breaking of these strands. You have no size evolution of your droplets.
No, I didn't measure the droplet sizes. However, Yes, I didn't measure the droplet sizes afterwards.
So in all the cases where that you have here, you always elongate the drops and they relax to the spherical shape, which is something which is very close to previous, so to the first stage.
Yes.
Okay.
Sorry.
Yeah.
But maybe you should explain what happens when you share an H solution, where the droplets are already big. What happens then?
Yes, when they are continuously shared,
Yes.
there's and then but there is still aging going on, even at the very high shear, but this aging is very slow, and thus with the alignments later on they will form continuous phase forming, and then at the end it will form phase separation.
It's not what I mean. When the solution is aged, you start with big droplets. And you just do the same thing you do here. You share it short time and you stop.
Breaking of the droplet.
What do you see then? So you start with bigger aged droplets, you do a bit of shear, and you stop.
Then they would, and then when I stop, they would again break into pieces, and
But do they form the pieces that you found before the shear, or without aging?
they would form. In the manuscript there is the rheology measurements that I did, where I performed continuous flow curve, and there was a slight decrease in the viscosity, even after multiple flow curve, showing that there is an increase in the droplet size even after the high shear, and when it went back to the low shear. So even after the continuous shear, we could see that there is a slight aging going on, or increase in the sizes going on after the breakup, and then they go back to the spherical shapes, but the droplet size would be bigger.
Because in classical dilution, when you shear, you may have two effects. Either you provoke some collision between drops and you increase the drop size, so you induce some coalescence by the shear. And in other cases, you can deform and break the droplet, so you go from large droplets to smaller droplet size. So shear can induce these two phenomena. And since you have very low interfacial tension, breaking should be very easy. So my question is really, what do you observe? Do you see some fragmentation when you apply shear, or they do not break, they just deform, and when you stop the shear, you have the relaxation to the earlier stage?
I think it goes more the first case, because when I looked into the rheology measurement, after the strong shear, the viscosity doesn't increase,
Yes.
but it decreases. So there would be an increase in the size compared to the initial before high shear was applied.
I agree with you. If you break, one would expect an increase of the viscosity or increase of the rheological properties that we do not really see, or very small. Okay. And so if I come back to the Pallier model also, because it's very interesting to use this model.
Yes, sorry.
Maybe what is not really clear is because if I remember correctly, in Pallier model you have different cases, depending whether the inclusions are really connected to the matrix or if they are not, and depending also on the interfacial properties. And so here I guess that you will make the hypothesis, or it's more a question, do you make the hypothesis that the interface is liquid? and has no viscoelasticity by itself.
Could you just clarify what you mean by interface is liquid?
Because if you take a surfactant, the interface usually is very liquid. The molecules can flow
Really well.
in two dimensions. When you have polymers, sometimes you can have some entanglements between the polymers, and you may have interfacial elasticity. And so here, I guess you just consider one constant for the interfacial tension, as you said. So does it mean that even if you have polymers, you consider that you have an interface which is completely liquid? And which of the case did you consider here? Is it the one where the inclusion have no interaction with the matrix? So what are the, in fact, what are the hypotheses behind?
The assumption, and not assumptions, hypothesis that I did with the Pallium model is that first that there is no coalescence within the emulsion, and that it depends on the monodisperse size of the droplets. And that we would focus on the ratio of the interfacial tension and the radius.
Because if we consider this model, you have a distribution over the size. So you have, in fact, you have different parameters. So I think in the manuscript, you didn't really use it the same way because you deduced interfacial tension.
Yes,
So here you also do it by considering that you take the radius from the confocal microscopy pictures.
Yes.
And maybe one question that what is the sensitivity of the model towards interfacial tension? I mean, if you change it by a factor 2, how does it change with the fit? Is it much worse or is it almost the same? So what is the sensitivity towards fitting with the parameter?
Actually, how you approached in the manuscript was not accurate. That's why I presented a slightly different distribution in the presentation. That there I showed the distribution of the radius, but here I showed the distribution of the R over gamma. So it wasn't from the fits, the values that they gave was the ratio of gamma over R, not just separate interfacial tension and radius. So this interfacial tension is actually depending on the radius. And so how I got this distribution is by first, when we fit the Pallium model, we give the arbitrary numbers of, in the beginning, I gave the radius of 25 microns, where with that radius, the interfacial tension that they gave was about 30 micronewton per meter, which is not the values that I calculated here. So those numbers that I put in arbitrarily, it's not exact or precise, but the important is the ratio between them. So from this fits, the distribution that I got is the R over gamma. So the sensitivity to interfacial tension is depending on the radius. And thus, from the confocal images, we were able to deduce the average radius. So that's how I got the interfacial tension. Yes, and this is the first time fitting the Pallium model to a very low interfacial tension. So it could be very, we weren't not sure if we could get the interfacial tension within the range, but I believe we got the interfacial tension within the range.
So I really would like to congratulate you for all the experiments you did. I think Maybe we don't really see everything, but I guess it's a huge, it's a lot of work. And I really would like to congratulate you for the presentation of today. That was very nice. Thank you. Thank you. Okay, no, okay, let's go to this one now. The lessons that we will collect.
Mhm.
Yes,
Thank you. Thank you very much for your presentation. Thank you very much to the lab for inviting me for this jury. Yes, so it's a very nice work, have a lot of data. And I really appreciate your presentation because the way you explain, you change it, your order as said, Veronique. Yeah, and you really take some bits of information which makes more easier to understand. Like I think you had curve that you didn't mention in your manuscript, right? There's some stuff that some curve, for example, for shift factors. I think I didn't see that in the manuscript, right?
Yes,
So some
yes.
new stuff,
Yes.
very interesting, that makes it clearer. Just to comment very slightly on the manuscript. Yeah, there's some part maybe you can cover it later, for example, some the equations, some stuff you could explain more what the different parameters are at the very beginning. Sometimes it's blatant, but it's better if you really write everything. And I want to here in the presentation, I really explain, for example, why I have chosen two different solvents for the organic solvent. When you do the rheology,
Yes.
you have taken TPNT ether. I think it's not very clear in the manuscript why you have chosen this, but you change the solvent. So I appreciate what you said here, but you said very quickly. Can you say it again, please?
Yes, of course. So in the stabilization of PSPMA emulsion, I used THF solvent, which has a boiling point of 70 degrees Celsius. So it's very volatile. Even during the measurement, I could see the evaporation. So I had to add the solvent based on the mass. And also, but thanks to its volatility, it's very, it has a less viscous. So during the light scattering measurement, we always have to filter the sample. So it was, and at high concentration that I'm working on with the polystyrene PMMA, they make the solution very viscous. So it was easier to use a volatile solvent. And then, but to do rheology measurements, I wanted to conduct for 12 hours, which is impossible with the volatile solvent. And because I don't stop during the measurement, I continuously do it. And I cannot just add the solvent like in light scattering measurement. So I used much non-volatile solvent, which has a boiling point of 300 degrees Celsius. But this wouldn't have been useful for stabilization of emulsion because it has a very high viscosity. It would have more complicated to use in other measurements. So that's why I used a different solvent.
Yeah. This kind of explanation would be great to see in the manuscript just to understand where to switch from one solvent to another.
Yes.
So, thank you for explanation. And just because you talk about this Pallian model, why did you choose this Pallian? Because in the paper or in the literature, you mentioned in the state of the art, you say there are other models. And finally, you took this one, but you didn't say really exactly because at the end you have the Choi model, for example,
Yes.
which sound maybe not quite good too. But so why did you choose this one?
Yes, because this model there aren't many models that are connecting the interfacial tension and the radius droplet size distribution already. And for example, for Taylor, it's talking about the Newtonian solvent. And for the Detroit, it's not talking about the interfacial tension. And thus, the only model that are connecting this volume fraction, interfacial tension, and radius was this model. And so I used this model.
So really, what's your goal really using this model for doing this study? Is it just for people to measure the radius indirectly? Is it really the purpose, or because if we really want to do that, you could just measure it and that's fine? So what's the purpose really of this biological study?
Yes. First, by knowing one or the other, we could deduce interfacial tension and radius. Yes, but radius can be known by the confocal images or other measurements. But with the emulsion and common solvent, it's very tricky to measure the interfacial tension because in my case, the mixture of PSMA in dibenzyl ether, they are very viscous and they have a very similar density. So it's complicates to use other measurement to measure. For example, I tried to use the meniscus between the two faces to calculate the interfacial tension, but it was almost impossible because they had a very similar density. And I also tried to use the droplet relaxation method, where polymer shows the viscoelasticity that it shows the much lower interfacial tension than it shouldn't be. It should be. That's what I showed in the materials, I think. That's why I removed it in the presentation because it's not reliable. So I thought this method would be more reliable to reduce interfacial tension. Plus, we could know the distribution of the radius. And in this project, we're studying underaging. So there's evolution of the droplet growth. So if we could assume that the distribution is same during the aging, then if we know the average, then we could know how this shifting is going on, shifting of the distribution.
Yeah, but it would have been very nice to see that, because sometimes in the material itself, you describe the way to measure interfacial tension.
Yes.
After that, it was like,
Yeah.
how did you use it? I mean, there's nowhere in the manuscript where you use reading. There was like, why? I mean, if you say that, you say, okay, I tried, it failed, and that's why I'm using this. It would be like more interesting for the usefulness of this.
Yes, I'll add to the manuscript.
And so the other question, I mean, so you really couldn't measure any interfacial tension with
no, unfortunately.
Yeah, I understand. Because at 3.5 millimeter meter, right? 3.5.
Yes.
Even if the pendant drop, you could do something. You would be at the limit. The pendant drop, you could measure something.
Yes.
C'est pas des milliers.
C'est des micros, pardon.
Yes.
Excuse-moi, je vous prie. Ouais, 1000 milliliters would be good, but micronewton would be possible. Sure. Yeah, so about the stability of your emulsion, you say 1 week.
Yes.
Did you try 2 weeks or 3 weeks? Just maybe you didn't mention the manuscript. Yeah.
Yes, for water in water emulsion, when I came back from vacations, they were still stable, but I didn't record it as like scientifically because we know that recurring emulsions, they're very stable once they stabilize the emulsion. And also to keep track of those times, we thought 1 week is enough to understand the stabilization mechanism, and if it stabilizes on the same way between day 1 and 1 week is enough to understand. And for the other system in THF, the solvent is organic solvent, so there's a risk of evaporation with longer time. Even during the that measurement, I had to put the nail polish to avoid evaporation, and thus it was tricky to use the organic solvent.
The step of the art you mentioned, you have a nice discussion about calorie number, but then you don't use it afterwards. I mean, could you use it in the chapter?
Yes, but in the model we didn't use the Kaplan number because we were not using it in the model, so that's why I didn't use it in the interpretation. Yeah.
So it may be interesting to take that.
Yes,
I understand.
I
And it's limited. And in the virtual chapter 2, you mentioned both aging and rejuvenation, and there's a graph. It was a bit hard for me to understand. It was only the manuscript. it wasn't the case. Okay. Okay, where you change the maximum shear rate after 1,000 second minus one. And you have your flow to the viscosity curve, and then you have your stop at 100 or
The 500, yes.
That's 150 seconds.
Yes.
And Swan, and just can you just say why you did that?
That was to see the observe if there is aging on the flow curve. So even when we sheared it to the highest shear rate, and even when we only sheared it to 1 second minus 1, we were able to see this rejuvenation. So the viscosity goes back to initial state. And well, there was a few decrease in the viscosity. So there is a bit of aging, but still there wasn't much change with the time. And that was to be compared with the shear measurements. Because in shear measurement, we could just easily observe the aging. And thus, from confocal images, also even at, we can see that at 1 second minus 1, they're already forming the strands. So doing the flow curve until 1 second minus 1, 1 second minus 1, they were changing the structures already. That's what I wanted to show. Yes.
And are you studying thixotropy after all? Because you say rejuvenation, aging with thixotropy, you are trying to.
No, that wasn't that wasn't in the plan of the experiments, because here we were just studying the evolution of the emotion. But it would be interesting to see what do you mean by, if we could interpret it to more in the thixotropic.
Really about during time, we just share, but we have constant share, right? And you see how your product is evolving.
Yes, at the steady shear, you
Yeah,
mean?
addition.
Yes, we saw this evolution of the viscosity at steady shear.
Yeah.
This
We have several flow curve, but you
Yes.
can say, okay, at one shear, you have different viscosity.
Yes. That was to show that there's an it takes time to go to the steady state, but pseudo steady state, because they're evolving anyway. So it's never steady state, but it was to show that it takes time to achieve the steady state of the deformation at each shear rate. And at low shear rates, they show even huge deformation. And in one case, we had to wait until 900 seconds for it to achieve the pseudo steady state. But in the flow curve, we cannot do measurement at each point for 900 seconds. Thus, that's why we know that there's that they are not achieved in steady state, but still we're performing in the flow curves at this time period. It was 90 seconds, I think. So we have to keep that in mind when looking at the flow curve. That's what I wanted to mention.
But I was just thinking of when you change, because you have this nice evolution of your morphology,
Yes.
you could maybe compute the time it takes to after you enter the shear rate as you look here, the time for the system to go back to its initial state, for example.
Yes, that I could visualize it too. Yes, thank you.
And so this you mentioned the different emotion, different effect, of course.
Yes.
And that's true, but in the last chapter, it's not that you didn't say it's different. So you said clearly in your oral presentation, which is nice. So I was wondering, when they discuss about it, what kind of aggregates is it exactly? And what kind of is it kind of methods of stuff? Or is it a very solid particle? How would you say it's very solid? Or what kind of aggregate is it?
Yes, I didn't explain it in the slides, but I tried different things in the PO solution. I tried it to dilute it, and the aggregates remained in the PO solution, which means it can resist to dilution. I increased the concentration of PO and diblock, and that also increased the number of aggregates. And so what we assume it happens, and we even tried to mix it in the PO centrifuge, remove some aggregates by filtering, and through the confocal there was no aggregates anymore after centrifugation, but we put the dextran on that PO diblock mixture where it was able to stabilize the emulsion, which means there's again particle formation when there's an incompatibility between the PO and dextran. And we know that only small amounts of particles are needed to stabilize the emulsion. And thus, this particle formation is due to the incompatibility, mainly in PO, but also with dextran when they are in contact with dextran. And what we assume it happens in PO solution is that this PO-GMA is pretty rigid polymer. So there'll be a quick phase separation happening. And thus, and then quickly it will be stable by cross-linking among themselves, forming the myocytes and the aggregate, having the PO-GMA sticking out. And that is why we assume that is resistant to dilution as well. And yes, so that's what we think it happens.
Let's say it's not very dense, but could you evaluate from not configured, but at least see that really it's not very dense? Can you evaluate the density of the coverage?
I wonder how I could do it.
Picture of the droplet with the particles on it.
Yes. It's about micron size, the particles.
You can show how many there are on the surface. Here.
You mean density of all the
Yeah.
particles on the coverage?
It's easy to see on the picture. How dense it is, right? So,
Yes, because even I tried to make the animation, I tried to measure at the different Z, the height of through the confocal. They were very random, but they were very at a high population of particles at the surface.
Actually, I think they're relatively dense. Otherwise, it wouldn't work.
yeah, it can work when it's not so dense sometimes, but
Yeah.
very particular items. But yeah,
They're dense enough. They're no
Yeah.
holes.
yeah.
No big holes, at least.
For a more general question, then if you do it differently, you say I want to choose particles to stabilize this kind of solvent. Do you think what properties should have your particles? Do you know if what particle you could use to stabilize this kind of emulsion?
Yes, a lot of particles and has already been studied as well to the Pickering stabilization on especially on water in water emulsions. Like just not conventional silicon particles could be used. Like silica particles, yes.
Which kind of particle? Any silica particles or it should have very particular properties to stabilize?
Sorry?
Any kind of silica particle or should it have a specific property to stabilize the emulsion?
That I am not sure of the specific. I don't know which or what you're aiming to say, because
Well, you
For
can show the formula again and see what is important.
It seems that means that water emulsion stabilized by simple node from vacuum where they should change the amount of ACOH or use this kind of possibility.
Really one last question about so you have mentioned some application. Well, maybe one question. Could you use that in, for example, for biological or pharmaceutical application? If not, what you should change for this kind of application?
can I also re-answer back to the previous
Yes.
questions? Because we know that emulsion in common solvent has a very low interfacial tension, and thus and we know that the energy is depending on the radius and the interfacial tension. And to cover the interfacial contact, the particle size has to be big enough. And I wrote it in the bibliography that the particle sizes and the shapes matters. And not only spherical shapes works, there's also platelets. And so there's a very wide range of particles that can be used, as well as the polymers. And for the applications, you asked if it could be used in bio.
Yeah. From application,
From-
what should be changed? What would you do? If my question, like you were hired in the company, the pharmaceutical company,
Yes.
you say, okay, I love to work on water, yeah, less oil and stuff. But would you just say, okay, I did what I have done in my thesis, or should you change something?
For pharmaceutical industry, already our lab are working a lot with the food degrading ingredients using the pulenlan or gelatin in the system. So water in water emulsion consisting of dextrin, pulenlan, dextrin, gelatin. So they themselves can be used in food, which means it can also be used in pharmaceutical. But also in pharmaceutical, it can be used as like encapsulation. And if we could, because for the ingredients, there are a lot of ingredients that are bioactive, or which also it is active, very active ingredients sometimes, and they want to be oil free. So this water in water emulsion could be used.
The product could be the system could be.
For dextrin and PU, I think yes, but not for PSPMA. Of course, the solvent has to be changed. For it maybe could be changed to ethyl lactate, more greener solvent, but not the same polymers, of course. And to be used in the other industries, using this other system, there's a lot of studies on polymer blends without the solvent. So knowing how, and there are a lot of studies done on evaporating the solvent to prepare the polymer blends. And how evaporating the fast and that it can control the morphology of the polymer blends, and it's very sensitive. So it could be used in this application. Yes, I think.
Well, thank you. Again, thank you very much for your work. We have a very extensive work, and it was very nice in the work we have done two different kind of class of tournaments. And well, it's a very nice work. So thank you very much, and thank you again to your directions.
Okay. So, vous avez Professor Stefan?
Thank you, and thank you. First of all, I want to thank Lazare, Frédéric, and Taco to invite me today, and also to ask us to participate to the Rainier Whitecaps project. More precisely, we have to produce dextrin, PU, and copolymer, and you use them to stabilize the dextrin, PU emulsion. I always appreciate the discussion we have to explain the results. And sometimes I don't understand how it works, so I still have some questions. But first, I want also to congratulate you on your slide, your speech today, and all your research. So I have some questions, and maybe for the first part of your presentation with the dextrin emulsion. You studied the effect of the concentration of the polymer to stabilize this emulsion, and in your manuscript, but also in some slide, when you change the concentration, always you have, let's say, a presence during the first day, and after the diameter are stable. For many concentration the droplet size is around 14, 15 micrometers.
Yes.
And in case of 0.1 percent weight of the copolymer, for example, you have diameter around 80 micrometers. How
Yes.
you can explain that?
Of having the droplet radius of 18
Yeah.
microns and
Depending on the concentration, you not have the same diameter.
yes,
This
because I have it in this here. Why there? So you're asking why there is a droplet size changes by the concentration? Because with higher concentration, there's more particle formation happening, and thus it can, when there is a coalescence happening, the droplet growth of the emulsion, and the particles, they take time to surround the droplets and to stabilize. And thus with more concentration, it would go faster to the barriers, to the surface of the droplets. And that's why with faster time, it will stabilize the droplets quicker, so the coalescence less happened, so the droplet size would be smaller.
On page 98, you have more concentration. And lastly, if you use 0.3 waste crossing, but we observe diameter around 50, 48.
Yes, I think that's a mistake because I measured the droplet size of the stabilized droplets, but actually there is a huge phase separated phase happened at the bottom, so they don't really count. It's just the sizes, but we can observe the phase separated phase, so we can say that the emulsion is not very stable, that the copolymers are not effective. Are not enough.
When you explain this stabilization by the formation, the production of aggregates in the PAO phase, and you explain that this aggregate stabilize emission by Pickering mechanism.
Yes.
Do you have any question by Nicola? Do you estimate the diameter of the aggregate? Is it possible to estimate it?
Yes, I measured it, and I'll be adding that into the next article. When I measured the sizes, it was about 0.9 to 1 micron, and I measured about 30. When also for the droplets, when I measured the sizes, I measured about 30 droplets or particles per images, and I take about 3-4 images. So and in average, I took about 0.9 microns, 1 microns of diameter. So it's pretty huge.
And Véronique, can I ask you one question about the dilution, and that's still not very well understand. Okay, when you dilute your emulsion, you say that you maintain the copolymer concentration.
Yes.
So it means that you dilute with a copolymer solution,
Yes.
you know? So how can you explain that you didn't observe a stable emulsion? It means that when you add water phase, you increase the size of the droplet, but you don't have enough aggregate to stabilize it.
It's more about the emulsion itself, because when we dilute the system, the miscibility of each phase increases by increasing the entropy, and thus even with more concentration, I think the particle formation would be even difficult, because even lowering only the PO molecular weight, it decreased the stabilization effect. And that is probably due to high miscibility of smaller molecular weight, and thus the rigidity of the copolymers to form aggregates decrease, and thus it less form the particles. And thus, with both concentration decrease, so there will be a less compatibility, less particle formation, and lower interfacial tension. So there will be a less stabilization effect.
Since it's the second or third time we are talking about this point, the huge, the big difference, not only this one, with the oil water and the water emissions, is that the coverage is not enough conditions to stabilize. Okay. So you can, for example, find in some cases that there is a total coverage of the droplets, but there is no stabilization. So the stabilization is not only related to the coverage of the droplets. And we have worked a lot on this field with backward and with binding, for example, and we said, so we found that the interactions between the partners and the interface is really important. May be much more important than the coverage. The coverage is necessary because if there is no partner at the interface, you are not going to stabilize. But it's not enough. So in some cases, we work with, for example, with Gerich in 2009, we found cases that we have a total coverage, really the total coverage of the droplets, but it's not stable. So we here, for example, at the first level, you dilute, you keep the concentration particle identical, you keep the volume fraction identical, okay. So you have enough droplets, particles, but you have, like the first level, the degrees of the superextinction, which is important to increase the energy of adhesion of the particle interfaces. So this is the first conditions, and in our case, it's going to decrease drastically, which means that delta G is going to drop drastically. So then you have a second reason, the type of interaction between the particle and the interface, which you don't know how to predict it or how to explain it, and depending on the type of particles and the polymers.
And which one is the dispersed one?
Yes.
That's another mystery.
Yeah.
Yeah.
In both cases, they are at the interface. One is stable, one is not.
Yeah.
It's a mystery. There are lots of mysteries.
Yes, because when we looked at the copolymers in the stabilized emulsion, we didn't observe those particles in PO continuous phase. So yes, they always go to interface, and we don't know the preference of these particles as well.
My last question. On the other system, you observe like PhD, you observe mice, and you say that the mice are swelled by the
Yes.
dispersed things, and you say, why in this two system you didn't observe the same mechanism?
Because this diblock copolymer of polystyrene PMMA, they are very flexible, and but the dextran PUEGMA is a rigid structure, and we believe with the bottle brush structure, it was easier for them to form particles, and plus there was incompatibility with the PO. Thus, before they form stretching, they stretch or be flexible at the interface, they are already forming particles due to the incompatibility.
The rigidity of the PO block is due to the PMMA backbone.
I think so. It's due to the metacrylate backbones. Yes.
So thank you for the question again.
Thank you.
Or is that
Thank you. Okay, just looking by your FP now, just one or two questions. That's not too long. Just my first question is when you go through the semester curve,
Yes.
The wall, the vertical shift.
Yes.
Okay, and what kind of properties in mixtures can explain this change in vertical shift? Classically, it's possible to have a horizontal shift, and the vertical shifts are very, very small. In the blood of corridor, for example, some in our case, it's more important one. According to you.
Yes, it was. We expected only horizontal shift because there should only be relaxation of the droplets during aging. I think it's linked to the viscosity because this complex viscosity yes, this complex viscosity has an equation of G prime divided by the angular frequency and add to the G double prime by the angular frequency. So having the complex viscosity barely changing, so the shift on both the numerator and denominator in that equation are same. So that's why there is a same shift horizontally and vertically. But in terms of in the compartment itself, it's still a mystery as well. Because we only expect horizontal shift, yes. Do you have any assumptions?
But you don't expect the system is still a viscous liquid. So it's relaxing inside, dominating viscous liquid. So the relaxation is dominated by the viscosity of the system. So it's just you add a relaxation of the droplet, which is a small factor, to a very strong thing, which is the background viscosity, which doesn't change if you age. That's why it's a very small change in viscosity. So it has to do with something.
It's like little contractions.
Exactly.
Yes, it's okay. Thank you. Okay, so the last questions. When it's about version of impressions. Okay, so you will perform steady shear mode and dynamic mode. Okay.
Yes.
So my idea is to superimpose steady shear mode with dynamic mode, because when you have shear steady shear mode, okay, you perform steady shear mode to a state, morphology state, okay, and afterwards, perhaps it's possible to superimpose dynamic mode just to see the difference of macromolecular dynamics just at this change of morphologies. Do you think it's a good idea? If the technique, if the test will be possible, okay, it's a good idea just to see about the change on the dimension of droplets, for example, because it's possible to when you perform this dynamic after an aging under steady shear mode to recalculate all the parallel model examples. So it's a good idea, not why, what's the limits of this idea?
I'm not sure if I
understand this.
fully understood.
You performed
Yes.
steady shear rate. Yeah, and
Okay.
so you will have a different elongation of your droplets and afterwards trend like morphology.
Yes.
And you say afterwards 35 seconds.
Yes,
35 seconds after
After.
35 seconds, okay.
At rest.
You see spherical droplets
Yes.
approximately. Okay. So the question is why? It's because you have ruptures and after coalescence, so it's just a change, a chance to have this spherical size. I don't know. And my question is, if you can apply dynamic mode at the end of the steady shear mode. Okay, so you
Yes.
store your steady shear mode, you apply dynamic mode
Mhm.
here at high frequency, for example.
Mhm.
Okay. And after you apply gate steady shear mode
Okay.
and apply dynamic mode and so on. Okay. Okay.
Okay.
A lot of times.
The dynamic mode, you're talking about the oscillation measurement?
Dynamic oscillation, yes, dynamic, yes.
Yes.
Oscillation.
Yes, yes, yes.
Yeah.
Yes.
Okay.
Okay.
And it's a good idea or not? What's the possibility if you perform this kind of test? Possibility of
So that procedure would elongate, form strands of the droplets from the steady shear, and then from the dynamic, which in my case, I performed it at linear regime. So the droplets would break down, would act as if it is in rest, yes. And then depending on the droplet sizes, it would relaxes at different frequencies. Well, smaller and a smaller frequency. And if depending on how long I do this dynamic, the coalescence and the droplet growth would happen. For example, my oscillation measurement takes 10 minutes, but in 10 minutes, they don't evolve that much. And then if I reapply the shear, then it will form again the strands. And then if it's done in multiple times, because even at steady shear for a very long time, there is an phase separation going on at the end afterwards, because strands and then the strands form thick layers, and then at the end it will phase separate. So adding the oscillations in between would maybe show the evolution of the droplet size, but I think it'll be tricky because every time when it rejuvenates, I mean, when applied shear, there could be a randomness, and so it will be interesting, I think, to try to observe this, how the morphology of the droplets evolve in between the steady shear. Yes.
thank you.
Thank you
So
for your questions.
it's the time for your first also. So first, to speak, so it's directeur de recherche.
Okay. Thank you. I would like to, before I talk about Jung, but say a few words about what have been discussed here in the project. First of all, this idea of taking a big block of polymer to stabilize these emotions seems extremely obvious. And so you might wonder, why has nobody done that? The reason is that it's not because people don't try. It's because for some reason it's not easy. I know that years ago, Fred and I tried it, and we quickly to connect to flexible polymer, and it didn't work. And one reason, I think, is that they were simply too small blocks. So the idea was, okay, we can't do this synthesis, let's go. But I let Lazar talk about this particular project. And now we learn another thing, is that it doesn't work if one of the blocks is rigid, because rigid blocks tend to stick to each other. And it could have worked, it would have been nice. But the nice thing is that you show that it can work in principle, but what you need is 350,000 connected to 350,000 and perfectly flexible. So the way to do it is in water solutions. So to make it work, is to find a diabroch by hydrophilic system which has flexible, huge blocks, and then find the copolymer or the water emulsion that goes with it. I don't know if that can be done. It would be interesting to try. I also learned here something that a little bit puzzled since we had the discussion with the design about it. It's with this one. Can you show the fit? No, yeah, just the fit.
At the fit.
The fit of the pavilion. You were there.
Yeah, sorry.
To go one beyond. And you explained the fit. Yeah, yeah. You explained well, we fit it only to this because then it doesn't fit. Now, in the pavilion model, as you mentioned, you can introduce the relaxation of the polymer. So then it goes up, but still it didn't really work out well. And what you said was it's not just the viscoelasticity of polymers in the phases, but you also have to consider that at the interface themselves, they can interact, which is not in the pavilion model.
It's in the pavilion model. Because in the pavilion model, the superstructure is also a complex number. So
Yeah, but can you put it in the relaxation time of the interaction?
It was in the pavilion model, but the people never or very hardly they can measure the viscoelastic properties of an interface. This is why in many cases they consider that it's a constant, that it's liquid, and they give a constant. So this is maybe another way.
So it's frequency dependent.
It's frequency dependent. Yeah, it's a viscoelastic.
So that's obvious a complication that we didn't put in.
Yeah.
For reasons because we simply didn't know how to put it in. But it's just to reassure you, these relaxations, they're gone after if you go to lower frequency, right? So then you don't worry about it anymore, and then you can take the simple assumptions of the panel. So that's why it's simply limited, and when we go and publish this part, we should explain that probably a little bit better. Now realize because so that was something I learned, which I appreciate. Now coming to you, I think it was a very tough subject that you had to deal with. I mean, the pavilion model itself is already a tough thing to do. To learn about water emulsions, to learn about phase separation, and then to get this, find out it works and be all happy, and then figure out that it doesn't work as we expected it to work. But then persisting and doing it, trying to make the microcapsules by connecting them, which is a lot of work. But the work that doesn't work, you don't see. It's always a painful thing in research. You only see the stuff that works when you talk about that, and the stuff that doesn't work, which is a lot of frustration and a lot of time, is not seen. Which I just want to mention there because the jury doesn't see all that stuff, which did, and I appreciate it. And I think you can't know all the ins and outs. I mean, we have done this for years and years, so we can answer these questions. But you did well, and you understand quite a lot. So I thank you for that. And it was a pleasure to. Thank you very much.
Thank you. First of all, I would like to thank all of you for accepting to be a part of the jury of Hyun. And concerning Jung, it was a real pleasure for me to be one of your supervisors. And we have to realize that it was not an easy task at all. Because even if you present it in a very nice way, when you split the stories, it was not the case in the everyday's life. You really have to juggle with water and organic solvent. It was very complicated, and you had to play with this both project in parallel, and you did it well. And I think it's because you are a really well organized person. And it was also not very easy because you faced a lot of problems. And as Teco said, we always show the things that are working and not the things which are not working. For instance, we have certain problem with the evaporation of the solvent. You have to find a good solvent. Then you have the contrast with the control code, all these kind of things, and you succeed every time with Smile. And I really appreciate working with you because all of these things. And once again, I would like to congratulate you for all the work you have done. Thank you.
Thank you. So, okay, now.
Okay, thank you very much. So first, maybe I have switching day.
Oh, yes, of course.
Because la fin je remercie le jury déjà d'avoir accepté de siéger ici avec des contraintes de logement, de déplacement très très compliquées avec je savais pas que le monde était aussi même que ça. Donc, voilà, donc, du coup, vraiment, je beaucoup apprécié aussi les rapports des rapporteurs et le travail que vous faites, toutes les questions qui sont là. À vrai dire, il y a quelque chose qui. Finalement, on démarre un sujet et puis on a des questions, souvent extrêmement simples. Est-ce qu'on peut stabiliser des émotions particulières comme ça, au en haut, ou des solvants un peu communs, avec des composants arabes? C'était une chose qui était extrêmement facile, en tout cas très commune dans le mélange de polymères, de WIPO, mais peut-on le faire ici? Donc la question est extrêmement simple, et on voit derrière tout le travail qui en découle, et surtout toutes les questions qui sont soulevées par ce type de problématique. Et on arrive à la fin, on a quasiment plus de questions que de réponses. On a appris beaucoup de choses, mais on a quasiment beaucoup plus de questions que de réponses au départ, en tout cas beaucoup plus de questions à la fin que ce qu'on avait au début. Et honnêtement, c'est ça qui, en tout cas, de mon point de vue, fait qu'un sujet est passionnant et intéressant. Alors, on a encore plein de questions. On se pose le modèle de Paléa, on voit que voilà, il y a plein de choses qu'on peut faire aussi avec, et ainsi de suite. Le sujet, effectivement, sur lequel on a commencé à travailler là-dessus, le premier papier, je pense, on a dû publier en 2009 sur l'émission haut dans haut des crimes. Et puis derrière, on a continué à persévérer parce qu'on avait un peu vu qu'il y avait un vrai potentiel pour moi de questions académiques fondamentales dans ce domaine-là. Alors que ça paraît effectivement deux mélanges incompatibles, mais le fait de remettre un troisième élément qui va diminuer les tensions de surface, qui va diffuser les interfaces, qui va créer des interactions en termes de temps et d'espace et de nature très très différentes de ce qu'on connaît dans les mélanges moléculaires, eh bien, ça fait que depuis 2009, on est en train de travailler là-dessus, et puis encore de plus en plus de personnes qui travaillent sur ce dessus. Et donc, et pour le sujet actuel, effectivement, on a commencé ici, on dit OK, copolymère à bloc, on a essayé ici, mais on n'a pas réussi, en tout cas, à faire la chimie qu'on voulait. Et puis en plus, c'était l'occasion de collaborer avec les collègues de Nancy, qui maîtrisaient sa chimie à l'eau. Et on voit que c'est compliqué. D'accord. Donc, beaucoup plus compliqué que chimie. Et qu'on voit effectivement, quand on pense avoir maîtrisé les choses, eh bien, il y a plein d'éléments qui nous échappent, aussi bien au niveau de la synthèse qu'au niveau de la physico-chimie. Et puis ici, donc, je reviens un peu à ton sujet, qu'on avait effectivement, c'était l'occasion de monter ce projet de WebCaps. Alors, il fallait les polymères. On a vu que c'était pas simple d'avoir les polymères déjà à la base. Et entre-temps, on s'est dit, il faut quand même qu'on avance et qu'on essaie de trouver une autre solution. Et c'est pour ça qu'on a shifté vers les solvants organiques. Donc, c'était quasiment au pied levé, mais il fallait déjà trouver le moment, et tu as extrêmement bien réagi à ce niveau-là. Parce que pour nous aussi, comme on avait déjà exploré eau dans eau et on avait vu que c'était quand même très très différent, il y a beaucoup de différence par rapport à l'huile et eau, eh bien, on pensait que de toute façon, avec un autre solvant organique, on aura aussi d'autres surprises. Voilà. Donc, on y allait, mais on savait qu'on allait être effectivement confronté à d'autres problèmes. Mais ceci dit, tu as extrêmement bien réagi, travailler sur deux sujets, c'est vrai que ça paraît à peu près pareil quand on le raconte, selon selon le commun. Mais dans les faits, la physico-chimie fait que les interactions, les organisations sont pas tout à fait les mêmes et ça change un peu beaucoup de choses. Les liaisons hydrogènes, les APA, les autres des émissions organiques, et voilà. Donc ça change un peu les éléments, les variables, et ça peut changer pas mal de choses. Donc, tu es venu aussi à la modélisation, le modèle de Palière. Donc, je veux remercier beaucoup François Lameuil qui nous a aidé un peu vers la fin pour mettre ça un peu en place, mais il y a beaucoup de travail de ma part à faire. Voilà. J'ai eu beaucoup de plaisir à travailler avec toi. Tu as toujours été extrêmement calme, d'accord? Même s'il y avait voilà, des hauts et des bas, mais c'était extrêmement super calme, on voit pas le stress, mais le boulot était là, donc c'est parfait. En tout cas, je te souhaite une excellente formation.
Merci.
Alors, on va délibérer, donc du coup, on va vous demander de sortir, on va rester là.
I'll leave the Zoom, but I will unmute and I will turn off the video. Yes.
It's correct.
Bonjour.
Yes.
You want to read the sermon in French or in English?
French.
French will be fine?
Yes.
Ah, c'est d'accord.
Elle est d'accord pour faire en français?
Yes.
Mais c'est
Après, c'est après, c'est juste.
D'accord.
D'accord. Bien. Bien, alors, madame, donc, bon, le jury a délibéré. Ça n'a pas été trop difficile. Nous avons beaucoup apprécié votre présentation qui était posée, claire, hein, vous avez une diction très agréable, un ton très agréable, avec des supports très didactiques, ce qui a été énormément apprécié. Il a été souligné que votre présentation a apporté un plus par rapport à le mémoire, a clarifié certains points, en a développé d'autres. Voilà, donc ça a été énormément apprécié avec des illustrations très bien pensées. Le choix aussi d'avoir procédé, enfin, certains choix par rapport à votre mémoire ont permis de bien cristalliser autour des points principaux. Et ça aussi était très soulevé, très apprécié. Voilà. Le jury aussi a apprécié le recul, la capacité que vous avez quand même, hein, la prise de recul, et même on voit votre évolution depuis le mémoire, c'est très clair. Hein. Et enfin, nous tenons à vous féliciter parce que vous avez répondu de manière réfléchie aux questions, c'est d'accord, donc parfois très précise, parfois avec quelques doutes, mais on sent bien que votre honnêteté scientifique fait que vous avez réfléchi à les questions et l'apport et vos réponses ont convaincu le jury. Donc voilà, je pense que on ne peut pas soumettre de mention ou quoi que ce soit, mais le jury tient à vous congratuler là, pour votre prestation. Voilà. Et donc vous délivrez. Et le titre, après la lecture du serment de docteur, alors c'est de
Le Mans Université.
Du Mans Université.
Merci.
Voilà.
So I would like j'aimerais bien exprimer mes.
D'abord, le sermon.
Ah, le serment, pardon.
Il tient.
I'm doing it for you. Alors, je lis juste là.
Oui.
Oui. En présence de mes pairs, parvenus à l'issue de mon doctorat de mon université, et ayant ainsi pratiqué dans ma quête du savoir, l'exercice d'une recherche scientifique exigeante, en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage, pour ce qui dépendra de moi, dans la suite de ma carrière professionnelle, quel qu'en soit le secteur, pour le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats. Merci. Je peux remercier. Merci beaucoup pour les objets, pour m'accepter, évaluer mes travaux et pour venir au moins de tard de Bordeaux, de Paris. Oui. Oui, merci avec votre temps et disponibilité et aussi le travail pour. Oui, c'était un gros différent sujet en plus dans le manuscrit. Donc, merci. Aussi, c'était chouette pour revoir Monsieur Nicolas Huang, parce que au début, on a parlé de commencer à tester ensemble, mais il n'y avait pas de financement, du coup. Mais à la fin, on l'a revu, à la fin de la thèse.
Aller chercher avec l'ambassade de Corée, c'est quelque chose qu'on pouvait faire.
Oui.
Mais l'attractivité du monde, la place aurait été pareil.
Merci beaucoup pour venir au monde. Et merci Jean-Luc aussi pour la collaboration. On a bien pas mal à discuter pendant la réunion et moi, il y avait beaucoup de parties de synthèse que j'ai pas compris et vous également pour la psychochimie et du coup, on a dû discuter et même je voulais exprimer gratitude pour ça aussi pour toutes les discussions et je comprends que la synthèse est un très gros travail et je remercie pour tous les travaux. And for my supervisors, I thank you so much that I really feel that I was lucky to work with you because en plus, all three of you have a very different characters, and that was even nice to work with. Frederick, he was always there for all kinds of basic questions that I have and repeated 100 times. He was always very enthusiastic to answer them without any hesitations. Thank you so much. And Lazar too. You were always very nice with me, especially on the reality part. You were always you helped me a lot to understand the concepts, and you also were very caring. Even though sometimes you were not in the mall, when you come back, you still ask, "How is your family? How is the life?" You also asked about the personal life. Thank you, and also Taco. Thank you very much for your supervising. I think I have a bad habit of going inside the dungeon, trying to figure out myself. I try to be independent, but it's a good way of being independent. But it's when I have good supervisors around me, I have to ask questions. And before I go too much deep in the dungeon, he takes me out and middle check if I'm going to the right directions, and that I learned that actually not the important thing is not presenting the perfect work, but it's more important to middle check in the procedure so that I'm going in the good directions. So thank you, three of you, for being my supervisors. It was a great pleasure and honor to work with you. And of course, my colleagues, thank you very much for being here today and for 3 years. We laughed and we shared our sorrows together. Of course, the 3 years were not always the happy moment, but we shared them together, and I think we were able to get over because we were together, and we had a lot of fun moments as well. Especially Maria, Colin, Navia, and Ellie, we started together. So we had the similar difficulties in the beginning and then in the middle. And then when we revised, yes, we had the same pattern of sorrow. So we shared those moments. It was very nice to share with you guys. And also, Navia, thank you for being my colleague. Preparing and organizing everything for me, and also be there when I needed this conviviality. Thank you. And also my dad, he came all the way from Korea. Yes, he took 20-hour flights. Yesterday he arrived and he prepared the foods for me this morning. And since last year, I think I was wondering, who will be there for my sotonongs? I don't have any relative or families here. And then he decided he would come and celebrate the end of my education together. So that was very nice of him. Thank you. And also other audiences, or for those of you who are online as well, many of you guys are not in the or even in this country. Thank you very much for being in this moment. I really appreciate it. And so, thank you. Thank you.
Very well.
Oh. I guess that you heard it before.
Merci. Bien, évidemment, c'est un très beau travail. Bientôt, il y aura une fois de Gates. Ok, toi, qu'est-ce que tu vas faire plus tard?
Surtout environ pendant un an de chômage, après, pendant les réalités,
Thank you so much for the nice. It was very nice. And I really appreciate what you've been doing. I really hope you will get things out of it right
Yeah.
Somebody's so pretty. You're so pretty. Finally done.
Et voilà.
Can I take picture with these people? Yes. With the background.
And then
With them.
there cannot be.
You cannot.
No. I think.
Or if I.
Wait.
Hey Sandra. Hey, how are you?
I'm good.
You're good?
Yes.
You ready? Yeah. Yes, you are, you are. I'm sure you are.
Salut.
Coucou, ça va?
Oui, et toi?
Ouais, ça va super. Est-ce que Hyunjun est là à côté? Vite fait.
Je suis là.
Félicitations, c'était trop bien la présentation. Parfait, magnifique. C'était trop bien.
Merci, c'est très gentil.
Un bisou.
Bisous.
굉장히 너무 멋있었어.
고마워.
지금 아침에는 브레이크 없어가지고 못했는데
아니야, 괜찮아.
마지막에 빠지는데 언니 너무 축하하고
들어준 것만으로도 너무너무 고마워, 진짜로.
멋있어.
고마워, 주혜야.
이따가 파리에서 만날 수 있으면 좋다.
그래.
언니 나 사진만 찍을게요.
아, 그래.
언니 너무 예뻐.
고마워.
언니가 일단 이만 가봐야 될 것 같은데 너무
안녕.
파이팅.
Salut, Maxime.
Salut! Ouais,
Merci d'être là.
Pas de souci. Etienne pouvait pas se rendre disponible parce que avec le décalage
Ouais,
horaire, c'est compliqué. Du
ouais,
coup, elle m'a
d'accord.
envoyé. Elle avait peur de pas comprendre grand-chose aussi, mais elle voulait vraiment participer. Mais
Ouais,
félicitations, c'était
merci.
impressionnant, super intéressant, très bien présenté,
Oh,
et il me tarde de voir ce que tu vas faire du coup pour la suite.
merci, c'est très gentil d'être là, visio même. Et j'espère qu'on peut se voir encore avec Étienne dans in the short period.
Oui, bien sûr, bien
Quand
sûr.
elle revient.
On essaiera de faire ça, on essaiera de faire ça.
Ouais, ouais. Et Corinne, je te vois. Ah, ah oui. Ok, ok, yes, yes. Ah, Colline, je te vois, je te fais salut. Et aussi, Lucas, Andrea, Suti, 안녕, 안녕, 오빠, 돈 오빠, Sai, salut. I have to go now to assist my juries for the podcast. So thank you guys for being here. I'll message you again.
Bisous, félicitations
Bisous,
encore.
merci.